types of alloy steels. First one is tool steel and second is stainless steel. So in today's class, we are going to study only tool steel. So the name itself, tool, you will understand the meaning that the steel which is used for making the tools. So these tool steels are of four types: cold work tool steel, hot work tool steel, high speed tool steel, and special purpose tool steel. Cold worked, it is missing there. So cold worked tool steel, hot worked tool steel, high speed tool steel, and special purpose tool steel. These four types we are going to study today. So main one by one, what are the contents, what are the properties, what are the requirements, and how these steels fulfill the requirement. All these things along with the composition are covered in this topic. Now friends, the meaning cold working and hot working you have studied in manufacturing process. So there are working, mechanical working, one is cold work and other is hot work. The meaning of word cold doesn't temperature. The meaning of word this meaning cold work is below recrystallization temperature. So when any of the working is carried out below recrystallization temperature, such working, such forming process is called as cold working process. And when any of the process is carried out above recrystallization temperature, then it is called as hot working process. Now there are separate requirements. So the steel or the tools which are using at cold working operations, it requires some different characteristics. The tool which is required to work at hot temperature or higher temperature, these are the different requirements. To fulfill that requirements, these categories are made and accordingly alloying elements are adjusted. So one by one, let us see. So first is cold work tool steel. It is written clearly, the tools working at temperature less than recrystallization temperature are made up from cold worked tool steel. I repeat once again, the tools working at temperature less than recrystallization temperature are made up from cold worked tool steel. So now you know that recrystallization temperature is different for different material, for different alloy. How to calculate recrystallization temperature for particular alloy? Let us consider we are working on one particular steel. I have explained you iron carbide diagram. Turn the pages back and see. There are, if you consider 0.008 to 2%, there will be thousands of steel. Just by varying 0.01% of carbon, type of steel will be, category will be same, but alloy will be different. For each alloy, there will be different melting point. So you have to draw the vertical line at that percentage of carbon, and that will be your melting point. Now, how to calculate recrystallization temperature? We have to calculate recrystallization temperature based on one formula. It is 0.4 T melting point. Means if any of the alloy's melting point is 1000 degrees Celsius, its recrystallization temperature is 0.4 times, means 400. This is simple logic. Means if you are working on that particular object, then your recrystallization temperature will be 400. And if you are working on that object at less than 400 degrees Celsius, you have to use cold work tool steel. On same object, on same workpiece, if it is a red hot condition at 800 degrees Celsius and you want to operate it by tool, then the tool which is used at 400 working temperature will not work at 800 degrees Celsius. So for that purpose, different tool is required, and that's why such tools will be hot work tools. let us see what are the characteristics of cold work and hot work. I hope you understand better. Now, there are again 4 categories of cold work tool steel. It is very interesting, friends. So, some hardening treatment is there, and you are going to familiar with it in the chapter heat treatment process. But as the reference came earlier, you have to remember it. So, there are 4 categories of cold work tool steel. Water hardened steel. Second, oil hardened steel. Third, air hardened steel. And fourth, high carbon, high chromium steel. I'll repeat once again. Water hardened steel, oil hardened steel, air hardened steel, and high carbon, high chromium steel. Let us see what is this concept. Now, first of all, let me explain you the process of hardening. Time being, you have to remember it, because detailed process of hardening I will explain in the chapter heat treatment. Now, you may understand the meaning itself. Hardening means making the part harder. So anyhow, we have to make the part harder. If we make the part hard, you can operate on other part. One interview question I will ask, somebody should answer. Whenever you are cutting any of the object, what is the basic requirement for tool and workpiece? Tell. I repeat once again. In machining process or in cutting process, what is the basic requirement? Question is very simple. Answer is also very simple. But if at that particular time when interviewer will ask such simple question, also you may not understand. Now I am putting this question in the platform. Tell me what are the basic requirements, or what is the basic requirement for cutting process? I will take anybody's name. Krishna Langote. Krishna. Whether Mr. Krishna Langote is there? If he will not respond, I will put absent. So Krishna Langote is absent. Then Sachin Kengar is there. Roll number 52. Sachin Kengar. Roll number 52. Sachin Kengar. 52 absent. Samruddhi Deshpande. Roll number 1. Hello. Roll number 1. Am I audible? Somebody speak without taking. So I am audible means other people are not responding. Roll number 1. Somebody drop message. Tool must be harder than workpiece. Very good. What is your roll number, Avinash?
69, sir.
60?
69.
Okay, very good. This is the basic requirement. Always remember, tool must be harder than workpiece. Otherwise, your workpiece will cut the tool in any of the machining process. So you convey the message to roll number 1, roll number 52, and Krishna Langote that they are absent. Okay. Now we will consider this aspect, and then how can we make the tool hard? So our basic requirement is we have to make the tool hard. How can we make it? There are a number of processes of making the part hard. One is heat treatment process, another cold working process, then another precipitation hardening. Then number of hardening processes are there. So we will not go in that depth. In this concept, we are studying how to make the steel hard by this heat treatment process. So hardening is one of the basic heat treatment process out of three: so annealing, normalizing, and hardening. These three are basic heat treatment process, out of which hardening is the process in which parts are made hard by heating and fast cooling. So if you heat any of the steel,
Hello.
what is problem? What is problem?
Sorry, sir. Hello.
Where you were?
Sir, you took my name.
Yes, I took
Hello?
my name hello, your name I have taken 5 minutes before.
Sorry, sir. There was network problem, so I have to rejoin.
You said you took my name and this disturbing your. Am I audible clearly? Somebody
Sir, I am having network issue. That is why.
Okay, in that case, you can put SMS in the chat box. There is a chat box. Okay, no problem. I will consider your attendance. So friends, we can make the steel hard by hardening process. So in hardening process, part is heated at some particular temperature, hold there for some time, and then quench. Quenching is fast cooling. So you might have experience. You can make any part red hot in any of the flame and immediately dip into water. You will find it will cool immediately. So this is the process called as hardening. So part is made hard either by forming the hard phase. Martensite, I have taken the name in previous class. So ferrite, perlite, and is lead burite, cementite. All these phases are present on FeF3 diagram, but two more phases are not present. That is martensite and bainite. These two phases are shown on different diagram. These two phases are harder than perlite. I repeat once again, martensite and bainite is harder than perlite. So if instead of forming perlite, if you form martensite phase, your part becomes hard. What is not microstructure, crystal structure of perlite? Can anybody tell? Anybody willingly? Aman Mulani. Aman Mulani. Whether Aman Mulani is present? Samruddhi, am I audible? Samruddhi, am I audible? If there is a problem, you put message in the chat box. Avinash Madne. Avinash Madne. Hello. Anybody can speak?
Yes, sir.
Who is speaking? Rhythm. Rhythm, am I audible clearly?
Yes, sir. Yes, sir. You are audible, sir.
Okay. Now, answer my question. The perlite phase we have seen on FeF3 diagram. It is hello. Perlite is combination of. Tell the answer.
Alpha plus beta.
Sir, hello.
Yes.
Alpha.
Alpha plus,
Alpha plus Fe3C.
correct. Alpha
Fe3C.
is Fe3C is cementite. It is called as ferrite plus cementite. So perlite is mixture of ferrite plus cementite. Ferrite is soft phase and cementite is hard phase. And in turn, as perlite is mixture of ferrite and cementite, perlite is harder by virtue of cementite. So as cementite is present, perlite is harder. If you compare ferrite and perlite, perlite is harder because perlite contains cementite. And if you compare perlite with pure cementite is harder than perlite because perlite consists of soft phase alpha along with Fe3C. This is simple logic. Now, more than perlite, what is harder? Martensite and bainite. So bainite and martensite are harder than perlite. If instead of forming the perlite phase at room temperature, if we form the martensite, then steel becomes harder. How to form martensite? Very fast cooling. So alpha plus Fe3C crystal structure is BCC plus orthorhombic. You can write it down. I repeat once again. Ferrite plus cementite, that is alpha plus Fe3C. The crystal structure is BCC plus orthorhombic. Now, instead of forming BCC plus orthorhombic structure, due to very fast cooling, structure will be BCT. I repeat once again, instead of forming BCC plus orthorhombic, structure will be BCT. The long form of BCT is body centered tetragonal. I repeat, long form of BCT is body centered tetragonal. This body centered tetragonal crystal structure is called as martensite. And this martensite is harder than perlite. So in hardening heat treatment, earlier at room temperature you have perlite structure in the steel. If you heat at higher temperature, it will form austenite, and again if you cool very fast, that will convert into martensite. I will show here, just wait. See, I am saying P is at room temperature. I am writing there, just check. If you heat, this P converted into gamma. Okay. Now you are at 1000 degrees Celsius because melting point of steel is very higher. Depends upon percentage of carbon, it will vary. Suppose you are at 900 degrees Celsius. 900 degrees Celsius, there is a solid, and that is austenite. So earlier room temperature crystal structure is BCC plus orthorhombic, that is converted into austenite. Means what? Tell immediately. Somebody unmute and tell. BCC plus orthorhombic at higher temperature converted into austenite. Means what? Tell. Somebody please immediately tell. What is crystal structure of austenite? You have forgotten earlier lectures. Crystal structure of austenite is FCC. Crystal structure of austenite is face centered cubic. So BCC plus orthorhombic is converted into FCC. You are at 900 degrees Celsius now. If you cool slow, again it will be BCC plus orthorhombic. Means austenite will convert to perlite. But we don't want perlite. We have to avoid BCC plus orthorhombic. In that case, it will be cooled very fast so that it will convert into martensite. And structure is BCT. Long form is body centered tetragonal. And this will be very harder than perlite. So if you are doing this hardening process by water, cooling in water, such steels are called as water hardened steels. I repeat once again, if you follow this heating, soaking and fast cooling process in water, then such steels are called as water hardened steel. Now, we have some notation. In that notation, W symbol is used. If you use the design data book, you will not find the word water hardened steel, air hardened steel. Roll number 59 is saying that not properly audible. Rohit Vidate, are you audible? Very good, you are writing. 59, you please check your network connection. No problem. So, if you are carrying out hardening treatment in water, such steels are called as water hardened steel. W1, W2, W3, W4, these are the symbols you will find in the book instead of the name. So, there will be tables called as steel handbook, design handbook in that way. So, what is W1? You have to, there is a series, big series, but one or two you have to remember for writing in the exam. I have taken W1, W2, 0.6% carbon, 0.6 to 1.4, range is given. This is water hardened steel. What is application? Drills, reamers, chisels, hammers, these are made by this water hardened steel. Now next one is oil hardened. So I have given this cycle: perlite, austenite, martensite. When you cool very fast, let us do the exam. No, everybody is at home. By safety precautions, do one experiment. If you make something steel part red hot on some flame, hold in the tongue. Don't hold in bare hands. You can take some cloth, etc., and make it red hot, and immediately dip in water. You will find a kind of sound in that way in Marathi. Sarr karun asa आवाज येतो. What is that? It is very fast cooling process. Because of this, there are chances of crack generation in your steel component. There is a probability that your part get distorted. It will lose its shape and there may be cracking. So why this is happening? Because of more delta T. So you are at 900 degrees Celsius and water is at 20 degrees Celsius. 900 to 20. 900 minus 20 will be delta T. This much 880 degrees Celsius temperature drop in 2-3 seconds. Because of that, there will be crack generation. There will be stress in the component. If you want to avoid this stress, because your mechanical components are completely manufactured and formed, and heat treatment is end process, you should not lose the shape and cracking will be generated in the component. Otherwise, you have to reject that part. So you have to take care of your part. How can we take care? Now water, what is limitation? 100 degrees Celsius. After 100 degrees Celsius, it will be evaporate. But there are certain oils whose boiling points, etc., and vaporization will be about 200 degrees Celsius. So if I will take bath, bath means one container where the coolant is kept. Take one temperature bath and I will put the oil. I can make that use of oil up to 150, 160, 180 degrees Celsius. So even at 150 degrees Celsius, oil will remain oil. It will not become vapor. Now, 900 degrees Celsius component, if I cool at 20 degrees Celsius water, see the delta T. And 900 degrees Celsius component, if I cool at 150 degrees Celsius, see the delta T. In both the cases, martensite is produced because martensite range is below 200 degrees Celsius. So by cooling in oil, what are the benefits? By cooling in oil, I am getting martensite. At the same time, chances of distortion and cracking, shrinkage is less. That's why to avoid this distortion, cracking and shrinkage, parts are cooled in oil. The steels which are made hard by using oil quenching are called as oil hardened steels. I repeat, the steels which are made hard by oil quenching are called as oil hardened steels. The steels which are made hard by water quenching are called as water hardened steel. One example, O series, O1, 0.9% carbon, 1% manganese, 0.5% chromium, and 0.5% tungsten. You have to remember this. So master tools, cutting tools, gauges, and one more thing, OHNS. OHNS is industrial name. You can write it somewhere and make star. This is oral question and interview question. What is OHNS steel? OHNS is oil hardened non-shrinkage steel. I repeat, long form of OHNS is oil hardened non-shrinkage steel. So this is oil hardened steel. Now remember, if you want to make the part hard, it should have hardenability. Okay, part is hard by number of ways. First thing, if you form the martensite, and second thing, if there will be more alloy carbides. Remember, I am telling the sequence. Perlite is, where is pointer? 1 minute. Perlite, then benite, then martensite, and then cementite, and then alloy carbides. Any alloy carbide, tungsten carbide, silicon carbide, vanadium carbide, molybdenum carbide. This is the sequence of hardness. Benite is more harder than perlite. Martensite is more harder than benite. Cementite is more harder than martensite. Alloy carbides are more hard. Actually, this is same. Iron carbide and alloy carbide. Iron carbide and tungsten carbide. Iron is one element, tungsten is one element, molybdenum is one element. So iron carbide, tungsten carbide, molybdenum carbide. If these quantities are there in more amount, if alloy carbides are more in amount, then also your steel will be harder. In some of the applications, I have very crucial component. I don't want to take the risk of shrinkage. So heating, soaking, and fast cooling. Even in oil, there may be little, we can't say that chances are not there. Very negligible chances are there. But to avoid every chance, I don't want to take that chance of shrinkage. In that case, this water hardening and oil hardening, or water cooling and oil cooling, both will be dropped and parts are cooled in air. In normal circumstances, remember, if see this upper cycle, perlite, austenite, and if you cool fast, it will give martensite. But if you cool slow in air, again it will give perlite. See at upper side I am explaining perlite to austenite by heating. If you quench in oil or water, it will give martensite. But if you cool again slowly in air, again it will give perlite. And perlite is not harder as like martensite. So what is third category? Third category is air hardened steel. Air hardened steels are quenched in air normally, not in oil or water. Then you will get perlite structure. Now I am saying that air hardened steels are harder than this other steels. You say how contradictory statement? Because air hardened steels are having alloying elements in more amount. So quantity of alloy carbides is more in air hardened steel than in OHNS and water hardened steel. I repeat once again, air hardened steels are the steels in which alloying elements are present in more amount. Air hardened steels are such steels in which alloying elements are present in more amount. So they form alloy carbides. Alloy carbides are harder than martensite. So we don't want martensite. If you try to form martensite, unnecessary you will coming across the quenching crack, stress, distortion. To avoid stress, distortion, quenching crack, I will cool in simply air and I will put more number of alloying elements. So now microstructure of air hardened steel will be perlite plus alloy carbides. I repeat, microstructure of air hardened steel is perlite plus alloy carbides, and microstructure of this water hardened and oil hardened steel is martensite. So third microstructure will give better hardness. That's why they are not cooled in the air or oil. Now there is question, or 3-4 times it was asked in the examination. Very simple question. You can write it down. Why air hardened steels are not water hardened? I repeat once again. Why air hardened steels are not water hardened? Second question. Why water hardened steels are not air hardened? Second question, I repeat, why water hardened steels cannot be air hardened? Now simple answer. Let us see first question, why air hardened steels cannot be water hardened? So air hardened, our ultimate aim is to make the part hard. This is the first statement. I am telling the answer. Our ultimate aim is to make the part harder. Air hardened steels are having more alloying elements. The hardness of air hardened steels is by virtue of alloy carbides. So we don't want to form the martensite. It is not necessary. Unnecessarily, if you want to cool it in water, then okay, you can form martensite plus alloy carbides. But in that case, unnecessarily you are coming across the stress cycles. Chances of crack are more. So if without quenching in water, just by cooling in air, our sufficient hardness is achieved, why to go for unnecessarily strict treatment? That's why air hardened steels should not be water hardened. This is the answer of question number 1. Now question number 2. Why water hardened steels cannot be quenched in air, cannot be air hardened? What is first requirement? First requirement is we want to achieve the ultimate hardness. Water hardened steels are the steels in which alloying elements are in negligible amount. So if you want to make that part hard, you must want martensite. If you will cool in water, perlite will convert into martensite and our aim is achieved. But if instead of cooling in water, if you cool in air, perlite will convert into austenite and again it convert into perlite by air cooling. And ultimately at the end, your microstructure by air cooling will be perlite. And as there are no alloying elements, so there is no question of presence of alloy carbides. So ultimate aim is not achieved by cooling in air. Hence, water hardened steels cannot be air hardened. I hope you understand. And in between, if you want to compromise, that is oil hardened, OHN steel. So remember, this cold work tool steel is more important. That's why I explain it more. Okay. Next one is high carbon, high chromium steel. Long form, I told, short form is HCFC. It is a D series. So it is an exceptional case. Somewhere I have written D4, 2.25% carbon. Actually, steels are not having more than 2% carbon. But these steel have more carbon and in exceptional case, it is 2.25. Percentage of chromium is 12, molybdenum is 1. These are extreme hard phase requirement. Coining dies, shear blades, punches. So you have seen how hard the dies should be. So for forming dies, coining dies, shear blades, and punches, they require very high hardness. That's why high carbon and high chromium. You can write long form. High carbon, high chromium. Okay, it will give very highest hardness. All these four types are used for the operation at below recrystallization temperature. That's why these are called as cold work tool steels. I hope you understand. Everywhere check W1, W2 means W symbol for water hardening, O symbol for oil hardening, then A symbol for air hardening, and D symbol for high carbon, high chromium. You have to remember this. Next one is hot work tool steel. Now there are two types of hot work tool steel and both have H symbol. The definition you read, the tools working at temperature more than recrystallization temperature are made up from hot work tool steel. Now this is not complicated as like cold work tool steel. So there was a concept, hardening, formation of martensite. That's why I have explained you in detail. So here tungsten type and molybdenum type. So tungsten is the main element and molybdenum is the main element. Hello, am I audible?
Yes, sir. Yes.
So no any concept like martensite formation, etc., etc. So tungsten tool steel and molybdenum tool steel. Tungsten and molybdenum, these are added and these steels are used for higher working temperature. So higher working temperature, see the application, hot extrusion dies, then forging dies, hot punches. So all these are common. Hello?
Sir, screen is not visible.
Screen is not visible?
Yes, sir.
1 minute. Huh? What has happened? One minute. Huh? I think that meeting is out. Just give me 1 minute. I will rejoin. Automatically it came out. Network issue. Just I will go on talking. By the time I will rejoin. So in hot work tool steel, the applications like forming dies, threading dies, coining dies. Here you require working temperature is very high, means above recrystallization temperature. So in that case, when working temperature is above recrystallization temperature, your tool should maintain the hardness. So very first question I ask you, what is the basic requirement for cutting operation? The basic requirement for cutting operation is tool must be harder than workpiece. Tool must be harder than workpiece is the basic requirement. And in that case, if due to higher temperature, the hardness will be reduced, then instead of cutting the workpiece, tool may get cut. And in that case, our cutting process will not be fulfilled. And that's why such elements are added in the steel, which is made, which is used for making the tool. The elements are tungsten and molybdenum. So tungsten and molybdenum, these two elements are added. And what is the specialty of tungsten and molybdenum? The specialty of tungsten and molybdenum is they can maintain the hardness at higher temperature. It will not allow to lose the hardness at higher temperature. That's why the steels which are added with tungsten, such hot work tool steel is called as tungsten hot work steel, and the steel which have molybdenum as a main alloying element is called as molybdenum type hot work steel. Now, what is difference? Both are almost fulfilling same thing. What is difference? So, difference is that tungsten is little bit costlier than molybdenum, and if you add more molybdenum, you can reduce the cost. Very simple. The capacity of maintaining the high hardness, is 1 minute. Whether screen is visible now? Just a minute.
No, sir.
The capacity of maintaining the high hardness for tungsten type is more than for molybdenum type. So if you use molybdenum as a main element, then in that case, molybdenum will reduce the cost. It will fulfill the work, but cost will be saved. I think it is visible now. Okay. So I request you to be there up to 10:05. I will ask next teacher to join at 11:05. 10 more minutes are required for me. So I was explaining tungsten type and molybdenum type. Both applications are same. Only tungsten is costlier than molybdenum. In that case, you can add more molybdenum. H is common. This symbol or series we can say. H20 is tungsten type tool steel. H41 is molybdenum type tool steel. If somewhere you read H20, so you have to understand H means hot work tool steel, and 20 some range. See 1 to 25 may be tungsten type, 25 to 50 may be molybdenum type. Accordingly, hello.
Yes, sir.
Yes, sir.
To 25 may be tungsten type, 26 to 50 may be molybdenum type. Accordingly, the range is given in the steel handbooks. So 0.35 carbon, 2% chromium, 9% tungsten. And you see in the molybdenum type, tungsten quantity is reduced and molybdenum quantity is added for saving the cost. Purpose is same. So this is hot work tool steel. And difference between hot work and cold work is hot work tool steel is used for working temperature more than recrystallization temperature, and cold work tool steels are used for working temperature less than recrystallization temperature. Third one is high speed steel. Short form is HSS. You might have heard this HSS steel. So high speed steel, very simple. If you are using your tool at very high speed and high temperature, it may lose the hardness. So what is the specialty? These steels can maintain high hardness at higher speed as well as higher temperature. Again same. Previous also it was tungsten type and molybdenum type. See, I will take back. This is also tungsten type, this is also molybdenum type. The series is different. This is H series and this is T series for tungsten and M series for molybdenum. If you see, the applications are tools, reamers, milling cutters, and one market standard name 1841. Remember this, write down somewhere. This is oral question and interview question, as well as it is MCQ question. So, hello. This is oral question as well as interview question and MCQ question. 1841 steel. Write a short note on 1841. What is 1841? 18 is 18% tungsten, 4 is 4% chromium, and 1 is 1% vanadium. You have to remember this 1841. It is a standard this composition used by the manufacturers for making tools, reamers, milling cutters. So this is as per the specifications, T series. Next one is molybdenum. Now, one more statement I have written with blue line. Molybdenum reduces the cost, but more tendency of oxidation and decarbonization. So you have to find a compromise between this. Whether you want to maintain your steel for higher speed for long time, then you have to compromise for cost. With tungsten, it will be little costly. But you have to save the cost. There are chances of oxidation and decarburization. Decarburization means there is a decomposition of carbides. When carbides are decomposed, hardness reduces. So that is the drawback, you can say. Applications are one and same. Tools, reamers, milling cutters. I hope you have seen the milling cutters and reamers. Yeah, have you seen reamer in workshop? If you make the drill of, suppose we want to make drill of 22 bore. In that case, we can take 20 mm drill, and this remaining 2 mm cut is taken by reamer. When you will come in workshop, you request your instructor to show the reamers. Milling cutters also you can see. Special purpose. This is last. As per the requirement, the steels are prepared for requirement of the making the maybe molds and other purposes. I want only shock resisting capacity to be increased. So in case of increasing shock absorption capacity, what are such applications? Punches, chisels, concrete breakers. So this is a S series. So 0.5% carbon, 0.8% manganese, 0.4% molybdenum, 0.2% silicon. This will give good shock resisting capacity. Hence, this combination is used for making punches, chisels, concrete breakers, etc. Then carbon tungsten tool steel. This is F series as per the requirement for broachers. Broaching is one more application in machine tool subject. MTP or studied broaching. Broachers are used for again making the slots, etc. And this is made up of this carbon tungsten tool steel, higher carbon and tungsten, which will give very high hardness for the teeth of broachers. Now, plastic molding dies are made by mold. This is P series. If you see any of the plastic component, in one stroke it is produced by the dies. That die is made up of steel, and it is called as mold steel. Sometimes you may read somewhere die steel. Spelling is DIE. Die means mold. So the steel which is used for making the dies is called as die steel. So more specifications are required to see the content, because die steel is vague word. So dies are any dies. So what type of die, whether it is a hot working die, whether it is cold working die, whether it is plastic molding die, accordingly the percentage are varying. So this is 0.1% carbon, then 0.6% chromium, 1.25% tungsten is used for making the dies. So friends, there is no option. You have to remember all these applications, because question is asked for 3 or 4 marks. Explain or write the short note on special purpose steel. Write a short note on cold work steel, or this reason as well as this difference in hot work and cold work. Or simply, if you see the old question papers, please give the composition, properties and applications of following steels. This question is always there. So you have to remember. These are some of the photographs for your understanding. See that upper left corner, I have shown the number of these cutters, reamers, drills, broachers, milling cutters. Now, can anybody tell what is this figure? This is wire drawing and rod drawing die. This is a cross section. So these dies are also made up of die steel. That is steel which is used at cold working. These are cold working operations. Okay. This is hot working tool steel. What is this die? Can anybody tell? This die. Immediately, we have less time. Rohit. What is this die? And you have studied in manufacturing process. Nobody is answering.
Sir, molding.
No. This is forging die. Forging die. Forging operation you have studied. Okay, this is upper and this is lower. And this is plastic molding die used for This is plastic molding die used for making the plastic bottles. Okay. These are some of the photographs for your understanding. Thank you. Hello. So friends, we will stop here. So you can just leave the class and you can join the next lecture. Thank you. Thank you very much. Ah,
Sir,
yes.
sir, the notes uploaded on the study material
You please drop in
are
WhatsApp.
not
It is not audible to
visible,
me.
sir.
Huh? Hello.
Okay,
Please
sir.
drop in
Okay,
WhatsApp.
okay.
I will reply you.
Okay, sir.
Okay. Thank you.
Okay.
Hello. Leave the meeting and join next meeting. Amol Mali. Next lecture started. Rohit. Rohit Chadge. Hello. Rohit Chadge.
Yes, sir.
दिग्विजय सर
Sir, I'm joining,
हे
sir.
कुठे ऑप्शन सापडणं एक मुलगा रोहित चडगे आहे की पण ते घेणं ते सांगता का मीटिंग इज बीइंग recorded but